Hi, I'm Professor Hank Dietz, and I'm going to be talking today about Tangled, a conventional processor integrating a quantum-inspired coprocessor. This work really began back in 2017 with the idea of trying to reduce power consumption dramatically by doing extensive bit-level optimization of computations. At the bit level, you can see lots of redundancies that aren't available at the word level, and it's possible to get as much as up to about 5 orders of magnitude reduction in the number of active gates to perform the same computation. However, quantum computing offers some additional benefits. So is there a way that we can obtain some of those? Well, in quantum computing, we have superposition and entanglement. Superposition means that a quantum bit, a qubit, has the ability to not only store a 1 or a 0, but to store a probability distribution for both 1 and 0. Well, if I combine multiple qubits in an entangled situation, if I entangle multiple qubits, what I get is that not only do I have it able to hold more values, but I have it able to hold all the possible values with an appropriate probability distribution associated with them. So for example, 16 entangled qubits gives me the ability to hold 65,536 separate values with a probability associated with each. Now, that means that we can save exponentially on memory use, and it also means that any gate that's operating on one of these qubits can actually operate on all of those values simultaneously with a single operation. So potential huge savings in power. Unfortunately, it's difficult to build a large quantum computer. There's limited coherence for values. You're not allowed to clone a value, and you can only use reversible logic gates. These are big constraints, makes it very difficult to get any real use out of them. So what we wanted to do is come up with something that wasn't simulating quantum computing, but was an alternative to it with similar properties. And that's what we think we have in parallel bit pattern computing. So the way that we represent a superposition is basically an array of bits. So here you see 2 pattern bits, 2 p bits, where the first one has 4 possible values. The second one has 4 possible values because it's two-way entangled. So there are 2 to the 2, in other words, 4 different entries for each of these. Entangled values are the ones that line up in the same array indices. We refer to these array indices as entanglement channels. So for example, here you can see what we've got is the two-way entangled pair of p bits that are holding the equal probable distribution of 0, 1, 2, and 3. All right. Now, this gives us a very effective data structure for representing superposition and entanglement, but it doesn't really give us any exponential reductions. The catch is that there's a lot of redundancy here. If we take a look, this second pattern is really 0 twice followed by 1 twice. The first pattern is 0, 1 twice. So by representing these patterns as regular expressions rather than as the actual bits, we can get up to exponential compression of that data structure, and we can operate directly on the regular expressions rather than on the arrays of bits. Now, we do this not at the bit level, but at the level of chunks of the AOB structure. So effectively, we still get our exponential speed up, but we still have relatively large chunks that we can operate on in parallel. So in parallel bit pattern computing, we're operating directly on compressed regular expressions, which gives us that exponential reduction in storage and gate operations. And we avoid the major quantum problems. We're forever coherent, error-free. Fan-out is not a problem. Non-destructive measurement. We can use any gates we want, not just the reversible logic gates. And we also get parallel AOB chunk evaluation using SIMD hardware. So the question is, how difficult is it to build that SIMD hardware that can efficiently manipulate AOB chunks? So to answer that, what we did was we built a proof of concept prototype of parallel bit pattern hardware, chunk hardware, called Tangled. And no, it's not the Disney Tangled. It has nothing to do with that. It's Tangled as the processor name because it's tightly coupled with a coprocessor that does quantum-like operations. And that quantum-like coprocessor called COT is basically implementing both superposition and entanglement. So we have an array of bits representation being manipulated directly in COT. The complete instruction set and toolchain for both was created. We also created multiple pipeline Verilog implementations of the full system. and we did extensive testing by simulation. And part of the way that we had so many pipelined implementations and so much testing was that not only did I create some myself, but we also had teams of students in the undergraduate advanced computer architecture course actually use this as their target architecture back in fall 2020 at the University of Kentucky. So here's what the Tangled architecture looks like. It's just a simple functional block diagram. Nothing really exciting here. When we add COT, you can see we're adding a fair amount of complexity. There basically is a somewhat unusual looking ALU here and such. So let's talk about what the COT instructions really are doing. Well, this is the list of the COT instructions, and I'm not going to go through each of them individually, but basically what you have is a relatively small instruction set that has operations working on 256 registers, each of which holds an AOB chunk. And that AOB chunk is 65,536 bits long, which means that anything that's 16-way or less entanglement takes only one chunk, but the software system above that actually supports up to 32-way entanglement as regular expressions using 16-way chunks in the regular expressions as individual symbols. There's no control flow nor any memory access for the COT coprocessor. All of that is done exclusively by Tangled. So relatively simple interface. In quantum computation, there are three distinct phases: initialization, computation, and measurement. Now, we don't really distinguish such phases, and we don't have to. However, in a quantum system, in the initialization phase, you can only set qubits to 0 or 1. They can't have a superposed or entangled value. So we can have a Hadamard operator, as they did, or we can have a Hadamard initializer, because we can use initializers any place we want. So basically, it makes more sense to do an initializer. And after implementing this as an operation, we realized, well, it would have been more reasonable to simply have constant registers, because we can always copy the values of the registers for 0, 1, and each of the Hadamard initializer potential values. So there are 16 such things for 16-way entanglement. Reversible NOT gates, the poly-X, which is just a NOT, controlled NOT, and controlled NOT, otherwise known as Toffoli gate, basically pretty straightforward to implement. And in fact, if we take a look at it, CC NOT is a little bit expensive because it requires 3 register reads. But really, CC NOT is nothing more than an XOR and an AND. So we can actually just implement it this way. So even though the hardware in COT directly implemented CC NOT and C NOT and so forth, it really makes more sense to just treat these as XOR and AND. Reversible swaps, namely swap and controlled swap, C-swap, otherwise known as the Fredkin gate. These are wonderful operations for quantum computers too, but they're really kind of expensive for us to implement, because swap and C-swap both require 2 register writes. And if you think about it, C-swap also requires 3 register reads. Now, it turns out that C-swap is a useful operation, and it's very expensive to simulate, so it might be worthwhile adding that hardware. But it turns out that the parallel bit pattern software infrastructure above it never actually generated that. When it was optimizing the gate level representations, it never actually generates C-swaps as an output. Consequently, there's no real reason to waste the hardware on implementing that directly. Measurement in a quantum machine is just random sampling, and it collapses the entangled superposed state. But that doesn't happen for us. So we created a measurement operator that basically takes an entanglement channel and simply reads the value of that non-destructively. If you want to randomly sample, all you have to do is pick a random number as the entanglement channel. However, the interesting thing is you can actually read out any values that you want by basically cycling through the different values for the entanglement channel that you select. That's not something a quantum machine can do. If you wanted to evaluate all of the possible values, all the possible results that were generated in one quantum computation, you're going to have to repeat that quantum computation multiple times. In fact, more than exponentially many times, because you don't have the control to guarantee that you're reading each of the entries. You just get random samplings. Whereas here we can control to guarantee that it only takes us exponential time to read all the values. But we can do better than that. So to try and sample an entangled distribution, There are various phase interference operations that you can do in quantum computers, and they're very complicated and touchy to implement, but it turns out we don't have that problem. We can implement these kinds of operations really cheaply because looking at an entangled superposition doesn't interfere with it. It doesn't collapse the state. So the operation that we've proposed and implemented is called next. And what it does is it simply, given an entanglement channel, tells us the next entanglement channel number that has a 1 in it from that object. This allows us to sample the state in very sophisticated ways, extremely efficiently. Here's an example of prime factoring of 15. On the right side, you see the word level code for doing this with the parallel bit pattern model. And on the left side, you see the actual assembly language code for Tangled and COT. And this was actually confirmed, does correctly compute the values. Just quickly acknowledging, there were actually 8 teams that independently created the pipeline Verilog implementations of this. These are the students who were involved in that. And Jordan, of course, was the TA and also deserves a little bit of applause for his work on coordinating everyone there. In conclusion, parallel bit pattern computing hardware is viable. We know that because we've built multiple Verilog implementations of it. And it is capable of implementing very efficient execution using bit serial SIMD hardware. In fact, it's disturbingly competitive with quantum computing, even though it's not quantum computing. The lessons learned, we've told you a few of them along the way here, but fundamentally, parallel bit pattern computing only needs a few unusual instructions. There are only a few things that we need for the hardware to support it to do this efficiently. And single cycle chunk ALUs are actually feasible. You can actually do all of these sophisticated operations within a single cycle. So thank you very much. And if there are any questions, I'll be happy to answer them live.